It's my pleasure to welcome virtually Carolina to our department. 2 years ago, Carolina, Eduardo Esteves, both from IMPA, and I got a grant from the Office of the Provost through their global initiative to establish a collaboration in algebraic geometry with IMPA, with the Mathematical Institute in Rio de Janeiro. Well, just before they boarded the plane, the pandemic changed our plans, but Zoom gives us a way to partially fix this now. So without further ado, I would like to introduce Carolina, who will talk today about a very broad and interesting topic, symmetries in algebraic geometry.
Thank you very much, Tony, for the introduction. And I would like to thank you for the also for the invitation. As Tony mentioned, I was supposed to come to the University of Chicago about 1 year ago, and that was my first trip canceled by the pandemic. So I hope that this visit is possible in the future, but for the moment, I'm very happy to be here through Zoom. And I would like, so let me now start sharing. Okay, can you see it?
Yes.
Okay, so so today I would like to discuss some notions of symmetries in algebraic geometry. Sorry, okay. And so this picture is just to illustrate what we mean by symmetry in geometry. So I just have here 2 pictures of algebraic varieties, and then you can guess that the first one, the one to the left, has a finite group of symmetries, while the second one, the sphere, has much more symmetries. So we are going to be looking at this type of symmetries in geometry. And in algebraic geometry, there are a few notions of symmetries that are interesting. And so in our context, we are going to be describing symmetries of a complex projective variety, which I will usually denote by X. So let me start by giving a first notion of symmetry, and that has to do with automorphism of projective varieties. So if you have 2 projective varieties, X and Y, then there is a notion of morphism between them. And then you can imagine that this is just a map between these 2 varieties that are, at least locally, they're given by polynomial. The coordinates of this map are given locally by polynomials. And then once we have a notion of a morphism, we have a notion of an automorphism of a projective variety, which is just the group of self morphisms of X with the composition. So for example, the simplest example is the example of, say, a projective space Pn. And in this case, it's well known that the automorphisms of Pn are just the invertible linear maps. So this is just PGL n plus 1 over C. In general, if you have any complex projective variety, then its automorphism group has a natural structure of a Lie group. And so one can look at the connected component of the identity, and this is a complex algebraic group. So this is not only a group, but it has a structure of a complex algebraic variety. And it turns out that, okay, we can subdivide our automorphism group into pieces. So if you look, so we can look at the connected component of the identity. As I said, this is a complex algebraic group. And then the quotient is a countable discrete group. And these 2 pieces may reflect different aspects of the geometry of X. So let me give you an example. So let me start with a very basic example, which is that of a smooth projective curve of genus G. So this is the same thing as a Riemann surface, as a compact Riemann surface. And we have this classical trichotomy, genus 0, genus 1, and genus greater or equal than 2. And this corresponds to the classical trichotomy of positive, zero, and negative curvature. This trichotomy is natural from the point of view of fundamental group and from many other aspects, and also automorphism group. So for the genus zero case, as we've seen, the automorphism group of P1, which is the Riemann sphere, is just PGL2C. And this is a affine algebraic variety. The case of genus 1, this is also again an algebraic variety. So these automorphism group, the connected component of the identity in the automorphism group is just also isomorphic to the elliptic curve X itself. So we know that the torus has a structure itself. It has a structure of a group, and then this automorphisms, and then we view this this X acting on X by translation. And then in the higher genus case, the automorphism group is always finite. So we have 3 very different behaviors. Affine genus 1, which is this is an affine group, this is an affine variety. Genus 1, this is a projective variety, is X itself, and genus greater or equal than 2, this is finite. So in general, in higher dimensions, we also have, we can also see different aspects of the geometry by looking at the automorphism group. So let me also discuss, before I move to the next type of symmetry, let me discuss a very interesting problem in algebraic geometry, which is that of describing automorphisms of smooth hypersurfaces. So by a smooth hypersurface of degree D, I just mean a projective surface in a projective space that is defined by a single equation of degree D. So in this case, we have this very nice theorem by Matsumura and Monsky that says that the automorphism group of such a hypersurface is always induced by linear automorphism of the ambient space, except in 2 cases. And these cases are when D is equal 3 and N equals 1. So that is exactly an elliptic curve, genus 1. And the case of N equals to 2 and D equals to 4. And in this case, X is what we called a K3 surface. So this is a quartic surface in P3. So except in these 2 cases, the automorphism group of X is just induced by linear automorphism of the ambient space. In the case of an elliptic curve, we have already discussed the automorphism group. In the case of a K3 surface, the automorphism group is always discrete, but it may be finite and it may be infinite. So it depends a lot on the surface itself. And so this is here we have a jungle of possibilities. But in both cases, the subgroup of the automorphism group that is induced by linear automorphism of the ambient space is a finite group. And so one question that we are going to address towards the end of the talk is, where do this automorphism come from? If they don't come from an automorphism of the ambient space, how can we describe them? Okay, so this is about automorphism. And now I would like to shift gears and talk about a different type of symmetry that comes from birational geometry. So let me just say a little bit about birational geometry. And for that, let me discuss the classification problem in algebraic geometry. So the classification problem in dimension 1, this was pretty much achieved by Riemann. So we have, as I mentioned, we have this subdivision into classes according to the genus. So in dimension 1, the classification problem may be stated as follows. So as a first step, we have this division into, we have this discrete invariant, the genus, and then we have, we put our varieties, our curves into these classes. And then for each fixed value of the genus, we look at the moduli space of curves of genus G. So now here we have an algebraic variety, or more generally, an algebraic stack that parametrizes these curves of genus G. So first we divide by according to some discrete invariant, the genus, and then we form moduli spaces. In higher dimensions, the classification problem is different, and basically because there are way too many isomorphism classes, so that in order to try to arrange them into classes in this way. And so let me explain this statement by discussing a very concrete example, which is the blow up of P2. So in algebraic geometry, we have this very basic and important construction, which is the blow up of an algebraic variety. So let me tell you first in words and then in equations, what is the blow up of the projective plane P2. So the idea is that we would like to modify our projective plane by removing a point and replacing it by a P1 parametrizing tangent directions at the point. So this is more or less what I try to illustrate in this picture. So we replace a point by a line of possible tangent directions. Very concretely, I can tell you in equations what this blow up is. So if I fix my point to have projective coordinates 0, 0, 1, then I can consider the projection from this point. So this is a linear map from P2 to P1. So I fix a line to be the P1, and then given any point of the plane different than P, I look at the line that connects this point to P and look at the intersection of this line with this fixed P1. So this in equations, this is just the map that sends the point with coordinates X, Y, Z to the point with coordinates X, Y. So this is a map that is not defined precisely at the point P. Now I look at the graph of this map and take the closure of this graph, and what I get is exactly the picture that I have to the left, the blow up of P2 in one point. And what we see here is that outside the point, I have an isomorphism between the blow up minus this P1, this line, to P2 minus the point. So this line is what we call the exceptional divisor, the exceptional line, which is the inverse image of the point. Now, I gave you this very concrete construction of the blow up of P2 at a point, but this construction can be made much more general. So I can take the blow up of any projective variety at a point P. And in fact, I can take the blow up of any projective variety along any proper subvariety. And the idea is always the same. I replace this variety, each point of this variety, by a projective space of normal directions of Z at that point. And so what we have in general is that I have an isomorphism between the blow up minus this exceptional locus, the inverse image of Z, and X minus Z. Notice that if X, for instance, if X is a curve and I blow up one point, I don't change the variety because I replace the point by the unique tangent direction at that point. So when you blow up points in curves, you don't see anything. The blow up is just an identity. So it becomes a non-trivial morphism only in higher dimensions. And this is exactly why the naive classification problem up to isomorphism is really not the right problem to address, because I can start, say, with P2 and blow up one point and then blow up a point in the blow up and so on. And in this way, I can construct uncountably many non-isomorphic surfaces. So the problem, so what we are going to do is we are going to classify varieties not up to isomorphism, but up to a weaker notion of equivalence, which is what we call a birational equivalence. So we say that two varieties X and Y are birationally equivalent if they have isomorphic dense open subsets. And so I will denote, usually we denote by a dashed arrow this birational equivalence. Okay, so now the problem of birational classification in algebraic geometry goes as follows. So given a projective variety X, the first task is to find a simplest representative in its birational class. So this is what we call in algebraic geometry, in birational geometry, the minimal model of X. So for instance, it's very easy to argue that if I have P2 and then I blow up a point, then the blow up is more complicated than the original plane. So we would prefer as a simplest representative the P2 rather than its blow up. And then once we have a simplest representative, this minimal model in a given birational class, we can try to construct moduli spaces of minimal models with some fixed discrete invariance. So this is the general problem, the classification problem in birational geometry. So I will not address the second part, the construction of moduli spaces in this talk, but I would like to say a few words about this finding a minimal model. So this is what we call the minimal model program in algebraic geometry. So the goal of the minimal model program is given a projective variety to find a simplest representative in its birational class. So in dimension 1, this was just as I said, there's not much to do for Riemann surfaces. So this was the work of Riemann in the 19th century. In dimension 2, this was achieved by the Italian school in the early 20th century. In dimension 3, this was a big theorem by Mori in 1988, and this is what yielded him the Fields Medal in 1990, of course, with contribution of many other mathematicians. And in dimension at least 4, this is the work of Birkar, Caccini, Haken, McKernan. I mean, this is the program is not complete in arbitrary dimensions, but there are enough results to have some classification scheme. So before I move on, let me just say one thing that is going to come up later. When I say a simplest representative, I really put an A because there is not in general a unique simplest representative. So usually we have to allow for non-uniqueness. So if you during the minimal model program, when you run the program to get a minimal model, you have to make choices at each step, and by making different choices, you may get to different simplest representatives. Okay, so now let me discuss another problem within birational geometry. So this has to do with the minimal model program, but there are also some special birational classes, and you may want to understand or maybe characterize the varieties that lie in these special classes. So for instance, there is the special birational class of the projective space. So we say that a variety is rational if it is birationally equivalent to a projective space. And a very important problem in algebraic geometry and birational geometry is to determine which algebraic varieties are rational. So this is maybe this is a too vague questions and maybe too wild, but let me put it in very concrete terms. So if you fix the degree D and the dimension n, one can ask whether the generic hypersurface of degree D in Pn+1 is rational. So here there are some very easy necessary conditions. So there are some easy birational invariants that one can compute. So an easy necessary condition is that the degree has to be low. So it has to be at most n+1. Okay, so this is one thing. So let us look then at small degrees. So the easiest example is the quadric hypersurface. So a quadric hypersurface, as I said, so this is a hypersurface in projective space that is defined by a unique equation of degree 2. And thus notice that because it is defined by an equation of a reducible equation of degree 2, if you have any line in the projective space, it will intersect this quadric hypersurface in precisely 2 points, or maybe 1 point counted with multiplicity 2. Except of course if it lies inside our variety. So that actually allows us to construct explicitly a birational equivalence between a quadric hypersurface and the projective space. So you just take a point and then you consider the stereographic projection from that point. Then this gives you a birational map. It's easy to check what are the dense open subsets that are isomorphic under this stereographic projection. And so this shows that, okay, so this shows that the smooth quadric hypersurface is always rational. And okay, so now let's look at the next case, the case of degree 3. And here already we have, you know, a very important open problem in birational geometry. So starting in dimension 4, it is not yet known whether the generic cubic hypersurface is rational. So we know that in dimension 2, a cubic surface is rational. In dimension 3, cubic threefold is not rational by the work of Clemens and Griffiths, and already in dimension 4, this is open. Okay, let me also, I don't want to say much more about this problem, but let me say that this is a very active problem in birational geometry, and we have been witnessing some very interesting new developments with tools coming from all sorts of fields in algebraic geometry. Okay.
Can I ask a question?
Yes, of course.
Yeah, just, and it's sort of from the style of your questions. There are all sorts of things that I feel like I should understand, but I don't. So for example, when you say the generic cubic hypersurface, is it clear that, you know, except on a set of singular ones, they're all birational to each other if I change the coefficients? I mean, you know, just the form of the question makes me realize that I'm missing some basic background.
Okay, okay, right. No, this makes sense, and this is what I mean here. Yes, what I mean here is that the question is it true that there is an open subset in the space of coefficients of the hypersurface, such that if I pick any coefficients in this open subset, this is a this will be a rational hypersurface. So in general, it's not known whether this is an open condition or this is actually it is not this. The condition of being rational is not necessarily an open condition. So, but so I am asking whether yes. So I'm asking whether there is this open subset in the space of coefficients giving you rational varieties. The answer is expected to be no. I should say, but we do not know.
And by the way, is it supposed to be harder the lower the degree is? I mean,
yes.
So that therefore, by concentrating on 3, you're just doing the ones that should be hardest.
Yes. Well, okay, I'm not sure. Okay, this is what people expect, and it's true that people have been there are many new, as I said, many recent results about this, and people have been starting from highest degree to lowest degree. So this is how the development goes in general.
All right, anyway.
Okay, thank you for the question.
Okay,
yeah, please, I should say that yes, please do ask questions. Okay, so now if you want to address a problem like this, so the one natural question is, which properties are invariant under birational equivalence? And here, remember, I would like, the title of my talk is Symmetries in Algebraic Geometry. So now we will introduce a second notion of symmetry. And let me just mention that we've been looking at the automorphism group. And for this particular type of problem, the automorphism group is not the right group of symmetries to look at, because the automorphism group is not a birational invariant. So suppose that you have two birational equivalent varieties X and Y, and suppose that you have an automorphism of X. Then you can compose it in this diagram with the birational map to Y, and you don't get an automorphism, necessarily an automorphism of Y. What you get is a birational self-map of Y. And so, and this motivates this second notion of symmetry, which is the one that I want to concentrate now, which is the definition of the birational group. So the birational group of a variety X is just a group of birational self-maps of X. And this one is a birational invariant. And it has been used to prove irrationality of certain varieties. So for instance, Iskowski and Manin in 1971, they used the birational group to show that any smooth quartic threefold is irrational. So they computed the group, the birational group of a quartic threefold, and they show that this is finite, and then compare it to the birational group of P3, which is huge. They could see that they are not birational. So this type of invariant is really used to address rationality issues. Okay, so now I would like to focus on the Cremona group. So this is the group of birational self-maps of Pn. So this is a very interesting group. This is a huge group. So let me just discuss a few aspects of this group. So let me start with what is known about the Cremona group of the plane. So this is a classical topic, classical object in algebraic geometry. And so, of course, the Cremona group, it contains the automorphism group, but it contains also other types of elements. So, for instance, this is an example of the sort of the simplest Cremona transformation of the plane, which is not an automorphism. So this is a map from P2 to P2 that sends a point to coordinates with coordinates x, y, and z to 1 over x, 1 over y, 1 over z. Or equivalently, if I multiply everything by x, y, z, it can be given by this in this quadratic form, and this is why it's called the standard quadratic transformation: yz, xz, and xy. So one can see from this description that this map is a involution, and it has a very simple geometry. So what it does, you can check using with this expression that it contracts. It's not defined precisely at the 3 coordinate points. So these are what we call the points of indeterminacy of the map, and it contracts the 3 coordinate lines to the opposite coordinate point. So this is more or less the geometry of this very simple involution, quadratic involution. So it can be a bit surprising that even though this the birational, the Cremona group of P3, P2 is huge, there is this classical theorem of Castingnovo that tells you that with the automorphism, automorphisms of P2 and this unique single quadratic transformation, you can generate the whole group. And I can say that this group is very complicated. So given any degree, I can write down a Cremona transformation given by monomials by coordinates in degree d. So this is a huge group. But nevertheless, it has this very nice set of generators. So this gives us a factorization theorem for the Cremona group of P2 that has been used classically to understand this group. Okay, so you may think that given this very nice description that that this gives you everything you want to know about this group. And okay, this is far from being true. And so I would like to illustrate how complicated this group is by stating 2 very recent theorems that answer some very basic questions about this group. So for instance, only in 2013, Cantat and Lamy showed that the Cremona group of P2 is not a simple group. So this question goes back to possibly to the 19th century, but only very recently we've seen the answer to this problem. Another very recent development is the classification of finite subgroups of the Cremona group. So this started with works of Bertini in the 19th century and was only completed some 10 years ago by Dolgachev and Skovsky. So this is just to illustrate that, and there are still many unknown properties of this group. Okay, so now I would like to move to the Cremona group in higher dimensions. So let me just make a contrast with the two-dimensional case. So I recall the Castingnovo Theorem for the Cremona group of the plane. And so it says that the Cremona group is generated by linear automorphism, so degree 1, and this one quadratic transformation, degree 2. And in contrast, Hilda Hudson already knew in 1927 that for in higher dimensions, for n at least 3, the Cremona group of Pn cannot be generated by elements of bounded degree. So any set of generators must contain elements of arbitrarily large degree. And okay, maybe I should also say that as far as I know, and as of today, it's still not known a nice set of generators for this group. So we do not have a strong factorization theorem as the one we have in dimension 2, given by the Castingnovo theorem. Nevertheless, there are tools that I will discuss later on to understand this group, and they have been very much investigated. And so to illustrate that, I would just like to state this very nice recent theorem by Blanc, Lamy, and Zimmermann. So again, they show that the Cremona group is not simple, but in a very different way. So in the two-dimensional case, Cantal-Lamy showed that the Cremona group of the plane is not a simple group, but any quotient was already known. Any quotient of the Cremona group of the plane must be non-abelian and infinite. So in contrast, Blanc, Lamy, and Zimmermann, they constructed this finite quotients of the Cremona group in higher dimensions. And to do this, they used a tool, they used a sort of a weak factorization theorem for the Cremona group that I will discuss a bit later in the talk. Okay, so so first I introduced the automorphism groups of projective varieties, and then I now discussed this different type of symmetry, this the birational self maps, and now let me just connect them by revisiting this problem that I discussed earlier, so automorphisms of smooth hypersurfaces. So remember, this is what I told you before, that for a smooth hypersurface of degree d, the automorphisms of X are always induced by linear transformation on the projective space, except in the case of a cubic curve, an elliptic curve in P2, and a quartic surface, a K3 surface in P3. So in these cases, the automorphism group might be infinite, while, as I mentioned, the subgroup induced by automorphism of the ambient spaces is finite. So where do this automorphism come from? So in the case of an elliptic curve, this is sort of a folklore result, which is very nice, that says that every automorphism of C, so this is an infinite automorphism group, so the group of automorphisms is infinite, but every automorphism of C is induced by a Cremona transformation of the ambient space P2. And now, what about the other case, the case of a K3 surface, quartic surface in P3? Then there is this question by Ghiza-Tullin and Ogizzo. Well, actually, the question was asked by Ghiza-Tullin whether every automorphism of S of a quartic K3 surface is induced by a Cremona transformation of the ambient space P3. So this question was at first, as far as I know, was first asked by Ghiza-Tullin, and it was addressed in this very nice paper of Ogizzo, where he answers it negatively. So he produced some very interesting examples. So he produces examples of a quartic K3 surface with cyclic automorphism group, and such that no non-trivial automorphism group was induced by a Cremona transformation of P3. But he also produced some examples where the automorphism group of the K3 surface is very complicated. Say it was, I think, if I remember correctly, a free product of 3 copies of Z2, but for which every automorphism is induced by a Cremona transformation of the ambient space. And so this is a problem that this is part of an ongoing project with Alessio Corti and Alex Massarenti, which is to describe the group of birational transformations of P3 that stabilize a K3 surface S, and also the group homomorphism from this group of birational transformations of P3 that destabilize S to the automorphism group of S. Okay, so what we do is we develop a framework to address this type of problem, and this is what I want to discuss now. So what are the tools that we've been developing to try to answer this problem? And so this is what we call volume preserving Cremona transformation. So this notion of volume preserving is, well, it's not new. So let me just give you an example. So one thing that you could do is you could take, for instance, this meromorphic volume form on the plane, the x over x wedge dy over y. It has simple, it does not vanish anywhere, and it has simple poles along the triangle. So the triangle here is representing the 3 coordinate axes, x, y, z equals 0. Then one can ask, okay, so what is the birational, so what is the subgroup of the Cremona group of P3 corresponding to Cremona transformations that preserve this meromorphic volume form? So this is what I denote in this way, the birational group of P2 with this volume form. So this question has been answered by Blanc in 2013. So he computed this group and he gave explicit generators for this group. So there is this first part, the part in pink and blue, which is the part that preserves the torus. So the torus, so this is a regular volume form in the torus. And so this first part, so we have the torus itself acting by translation, and we have the SL2Z, which is acting in affine coordinates, it's acting by monomials in this way. So this part of the group is very well understood. So this is the part that comes from the torus. And then you in order to generate the whole group, you have to add this Cremona transformation that has order 5. So this is a very special Cremona transformation that seems to appear in many parts of mathematics and in algebraic geometry. And so this is the group, this birational group associated to this volume form. And okay, here, let me just pose this problem because it will be connected to the previous problem that I stated. One natural problem is to generalize this theorem to higher dimensions. So to describe the subgroup of the Cremona group of Pn that preserves the natural volume form on the torus. Okay, so in general, we can do this not for the volume form of the torus, but we can take any meromorphic volume form on Pn, and we can ask, what is the subgroup of Pn preserving this volume form? Now, given any volume form, you could look at the cycle of what we call the divisor of zeros. So the zeros of the volume. Yes.
Just a quick question. If you take the previous problem and instead of the volume form, you look at symplectic form, but which is the sum of this dx over x, dy over y forms in pairs of coordinates. So that's also a natural problem, which seems to be kind of closer related to the theorem of blank. Is it known?
I do not know. I confess that I do not know. And yes, I don't know. I don't know the answer to this in general. If you fix,
thank you.
Although, if you see the symmetric form as a, Okay, so you can see the symmetric form is a equation in Pn, and then
sorry, symplectic.
Okay, sorry, symplectic form. Okay, so actually this Blanc calls this, the title of this paper is a symplectic birational maps of the plane. So yes, but I don't know if you take yes, I do not know what the answer should be in this case.
Thank you.
Okay, sorry. Okay, so now, as I said, we can do this for any meromorphic volume form, and given a meromorphic volume form, we look at omega zero. We can look at the zeros of this form minus the poles of this form. So this defines an element in the second cohomology group of Pn. So this is just a hypersurface of zeros minus hypersurfaces of poles counted with correct multiplicity. And it turns out that this cohomology class is always minus n+1 times a hyperplane section. So this is what we call the canonical class of the projective space. And just an easy remark that conversely, if you give me any hypersurface of degree n+1, I can always find a unique up to scaling volume form, a meromorphic volume form that does not vanish anywhere and it has simple poles precisely along x. So this is what I mean by this expression. And so now the problem the problem that I've been looking at with Alessio, Corti, and Alex Massarenti is to describe the subgroup of the Cremona group given by Cremona transformations that preserve this meromorphic volume form. So let me just put together these two problems that I have discussed that may look very different from each other. So we want to describe the group of birational transformations, say of P3 that preserve, that destabilize the quartic surface. And on the other hand, we want to describe subgroups of the Cremona group given by transformations that preserve a volume form. So what we noted is that in fact, this problem, the first problem is a special case of the second one. So whenever X is mildly singular, and okay, I may say what this is later on, then the group of birational transformations of Pn that preserve this hypersurface X is precisely the group of birational transformations of Pn that preserve the volume form associated to X. And for those that are familiar with the notions of the minimal model program, by what I mean by mildly singular is that the pair Pn together with this hypersurface of degree n+1 has canonical singularities. Okay, so this is a very this is not hard to prove, but this actually opens the door to many techniques coming from the minimal model program. So the minimal model program usually deals with meromorphic volume forms, and so this is what we call the canonical class of X. And so now we have all the tools from the minimal model program at our disposal to investigate this type of problem. And okay, so now I would like to explain some of the tools that we use in this framework that we've been developing, which is a factorization theorem for Cremona transformation. So as I explained before, in the case of the plane, we have the Castingnovo Theorem that gives us a very strong factorization theorem. You can factorize any birational map of P2 by automorphisms and standard Cremona transformation. So we do not have such a strong factorization theorem in higher dimensions, but we have a weak factorization theorem that is nevertheless very powerful. And this is what we call the Sarkisov program. So the Sarkisov program was proved by Corti in 1995 for threefolds and generalized to arbitrary dimensions by Haken-McKernan in 2013. And let me just explain very vaguely and philosophically what this means. So you are given a birational map psi between a self map of Pn. So this is this map on the top. And we do not know generators for the Cremona group, so we cannot factorize them using elements from the Cremona group. But the minimal model program and the Sarkisov program gives us tools to factorize this map. But what we do not have, this maps psi, so the maps xi, so the intermediate varieties are not necessarily Pn. So we have to allow for maps to other rational varieties, and this is what are called the Mori fiber spaces. And these are precisely the possible outcomes of the minimal model program when you apply it to a rational variety. So as I said, the end point, the output of the MMP is not unique. You make choices, and the outputs are what we call the Mori fiber spaces. So you have to allow for all these outputs as intermediate varieties in your factorization. And these maps are what we call elementary links. And they're called elementary links because they are really elementary. So these are the simplest possible birational maps that you can think of between these Mori fiber spaces. So for instance, this could be a blow up of a point in a projective space. Okay, so this is in general the tool that we have in general to study the Cremona group, and this is the main tool that was used to prove this theorem that I stated before by Blanc, Lamy, and Zimmerman about quotients of the Cremona group. But we also have the minimal model program also gives us a version of the Sarkisov program for volume preserving maps. So any volume preserving birational map of Pn with respect to some volume form is a composition of volume preserving Sarkisov links. So I do not want to I do not want to make this precise. But there is a way to attach to each of these intermediate varieties a natural volume form in such a way that this volume form is not too singular, is not too degenerate. So there is some singularity condition here, and these maps psi I, they preserve, they send the volume form to the volume form of the next one. Okay, so this is the main map, and then so we've been exploring this and to approach this problem. And let me just state two of our theorems. So the first theorem says the following: that if your hypersurface is very general, and by very general, okay, so this I put exactly precisely what I mean by very general. So first of all, I want this hypersurface to be smooth. And second, I want this Lefschetz type property. So I want that the second cohomology group of X is obtained by restriction of that of the ambient space Pn. So these are really the conditions that I need for the theorem. And when I say very general, maybe I should explain what that is that, okay, so we have this projective space of coefficients in my equation that defines my hypersurface. And when I say very general, I mean that there are countably many proper closed subsets that I have to remove in order to make sure that this condition is satisfied. So this is what we mean very general, the complement of countably many proper closed subsets. Okay, so this is the first theorem. So it says that if you want to use this type of tools, say to construct some interesting groups of the Cremona group, and this is certainly a very natural problem to construct subgroups of the Cremona group, then you have to choose a special hypersurface. Either it's not smooth or it does not satisfy this Lefschetz type condition. And then we went on and okay, then let's try to investigate what happens when you have a non-very general, so a special hypersurface, and this is this is the first case that we considered. So let's drop the smoothness condition, and let's take, say, a quartic hypersurface in P3 with one singular point, like a general one. I pick generic coefficients. So this is the equation, the generic equation of such quartic hypersurface. It has a singular point that locally looks like the vertex of this cone in green. So this cone in green is what we call the tangent cone to the surface at the singular point. So this is given by the equation A2 in green. And in this case, we have this restriction homomorphism. So we can look at the group of birational self-maps of P3 that preserve the volume form associated to S. As I said before, in this case, preserving the volume form is the same thing as preserving the surface. And so it will induce a birational self-map of the surface. So we have this restriction homomorphism, and we would like to understand this, the group and the restriction homomorphism. Okay, so the first thing that I want to say is that the group of birational self-maps of this surface is very easy to compute. It is just it is a cyclic group of order 2. So it's generated by this very natural involution tau. So let me describe this. So if you if you give me a value for x1, x2, and x3, then I can plug it in the equation, and then I can solve it for x0, and generically I will have 2 solutions. So what this involution does is exchange these 2 solutions. So this is the tau, and if I take my surface generic, then this is the only birational self-map of S. It's not an automorphism. In fact, it is a non-trivial birational self-map. So we have this, and then our theorem. Oh, okay. So this is just an example to show that this birational map, this restriction map, is surjective. So I can write down explicitly, and I wrote this down for you, a birational map. So the A and B are given by the coefficients of S. So this birational map can be checked to preserve the volume form omega, or equivalently, it preserves the hypersurface, it stabilizes the hypersurface, and we can also check that it is an involution. So what we get is that this, and it induces precisely our tau on the hypersurface. So we see that this map is surjective, and therefore, because it is an involution, we actually get a splitting of this sequence. So we have a restriction homomorphism from the group of birational transformations of P3 preserving the form to this cyclic group of order 2. We denote the kernel by G, and we have a splitting of the sequence. So this gives a structure of semi-direct product to this group. And actually, what we prove in theorem B is we determine precisely what this group is. So the group of birational transformations of P3 that preserve this volume form is this semi-direct product of G, and I will say what G is, with this cyclic group of order 2. And this group G is what we call a form of GM over this function field of P2. So this a form of G, so GM is just the multiplicative group. And when we say a form of GM over a group, we mean that this is an algebraic group over this function field, such that after a finite quotient, it becomes the multiplicative group GM. And okay, so but let me just say that these these tools, this volume Sarkisian volume preserve, this volume preserved in Sarkisian program, it does not give us just an abstract description of this group. We can actually write down all the elements of this group. So if you're interested in explicit explicit results, so here it is. So every element of G can be written explicitly in this form. And we, of course, we can also write down what are the elements in the other coset. So we can write down explicitly what are all the elements in this group. Okay, so this is our theorem B, and let me just finish by explaining how we want to use this tool in general to describe automorphisms of quartic K3 surface. So remember that we had this question, which automorphisms are induced by a Cremona transformation of the ambient space. And what we are doing actually, these tools actually allow you to, there is a very concrete strategy to address this problem. So if you give me the surface S and I want to understand whether its automorphisms are induced by the Cremona transformations of the ambient space, I want to describe this restriction homomorphism. So which automorphism, what is the subgroup of the Cremona group consistence of map that preserve this volume form and understand this this map. So for that, what I have to do is, well, if I have this map, if I'm given a birational map of P, well, here it should be P3. So of P3 that preserve S, it admits a Sarkisian factorization. And actually what we have to do is to understand step by step what are the possible links and what are the aspects of the surface that are involved in each of these links. So each of these links is a birational map, and it does something to S. It may do something to S, or it may restrict to an isomorphism of S. So S may not notice this psi. But the way that they are defined, they actually trace some curves on S, and then we hope to use this, try to use this information to address this type of problem. Okay, so let me finish this talk here, and I thank you very much for your attention.